north part. Okay, and there is a branch here, a part of the of the Gulf Stream reach the Labrador coasts and the northern part of Canada. And in this area, there is the release of the heat content to atmosphere. That's why the AMOC is so important in terms of climatic issues. And by doing this loss of heat content, the water densifies, and making denser, go deeper through in a specific area where the environmental conditions and the heat flux here are enough to create dense water that goes deep and deep in the water column, creating the so-called dense water formation processes. These processes takes place during winter, essentially, and contribute substantially to form the colder branch of the Adriatic Mediterranean of AMOC. You see here the stars. The stars are the well-known recurrent area in which recurrently this dense water formation process takes place. And they are in Labrador Sea, Immigrant Basin, Arctic Ocean. And we see that this is a simplified cartoon, that the pathways are much more complex or articulated. But in essence, we have a surface water warming the northern atmosphere. The surface water loses temperature. The heat content is flux are outgoing. The water gets denser under the local atmospheric condition. This dense water falls down and create the return branch of the AMOC, which is cool, is adjusted on the American coast and goes down up to the Arctic Ocean. And this is quite an interesting feature, and we see that are some potential correlation, at least in terms of area, with the tripole that we found in AMO. So the reddish part here is related to the northern branch of the Gulf Stream, the western part of the Gulf Stream, and we have an area which could be related to the intensity of the subtropical gyre, and then we have an additional red spot on the coastal Africa, which is could be related to the wind regime that is active in the east part of the on the Atlantic. And as we saw that AMO is quite strongly related to now, well, as sort of transitive property, now is always invoked to explain the variability of the air, sea, and ice freshwater fluxes between Arctic and North Atlantic. So, and is primary modulator water mass transformation processes. Probably has also an impact on the strength of the AMOC. But to summarize this point is AMO is a surface pattern, long-term variability. Now has a much faster rate of change. It has a lot of different scales overlap in atmosphere as usually, and but still the variability of the AMOC has some similarities, spatial similarities with the Atlantic multidecadal oscillation, and we see that at that scale the two are related or are strongly connected. Technically, AMOC is defining of the maximum of the overturning flux calculated in a predefined density layer. So we don't define the depth, but we define the end member of the water column in terms of density. Minimum density, maximum density. Sigma here means the density anomaly, which is quite a useful way to identify density, because density has variability which is quite limited compared to the absolute value. The density of the pure water is 1,000 kilos per meter cube, and the anomaly as the order of few per thousand. So density could vary from, say, 1,027 to 1,033, 34, 36. So for convenience, 1,000 is cancelled, and only the anomaly is retained. So the net effect here is equal. You have just a change of variable instead of rho. You have the reduced rho that's called sigma. So that's way to explain how this estimate is calculated. The second integral here is the spatial dimension. We assume that V is very meridional velocity field. The field that goes from south to north or north to south is integrated from west and from east. And obviously, this gives us a number, which is a transport, integrated vertically from two isopycnal and laterally from one coast to the other. And the only variable we have here is time. So AMOC again is a integrated value that explains the variability in time of this flux at certain latitude. AMOC is zonally integrated and encompasses both surface and deep current in the ocean. So as a single value for that. We saw that circulation is quite complex, but if you reduce it in one number, you can have such a similar similar value that can be compared, for example, with the AMO and so on. And we talk about NIO, AMOC, we already anticipate that AMO and AMOC are or must be related since they are active in the same areas, and AMO and AMOC exhibit, in fact, similar periodicity. So at the scale of the decadal scale, the meridional overturning circulation in the Atlantic and the anomaly of the surface temperature behave in the same way and are similar to other time series calculated for North Atlantic. So they are part of the same system. And for what regard now, you see here the now Hurley index, which is the typical way to characterize the conditions in the northern hemisphere of the Atlantic. And you see that there's no specific periodicity or evidence here, and extremely noise. But if you look at the power spectrum, you can identify cycles of 7, 13, 20, 26, and 34 years. They are overlapped. And so this is the almost white noise that you can find here, and we typical of the atmospheric processes. So you have almost all the scale of the decadal variability included in NIO time series. When to extract something more sensible, a clever way is to try to find a correlation between the two time series that you are interested to compare, in this case, now AMOC or now AMO, and see where the correlation is maximum by lagging one series compared to the other. So this is called time lag correlation analysis. And it's been seen that now anticipate the leading time series to NAMOC, AMOC, and AMO. This should suggest that now could explain, mechanically explain, or dynamically explain the variability of AMOC as a atmospheric force and field changes that convey the variability into the surface ocean. This is quite clear for what regard atmosphere-ocean interaction, but which is the ocean-ocean interaction? I mean, which is the interaction between AMO and AMOC? And in this sense, the explanation found with the correlation analysis was not so clear, because there are two different results. In the first part of the century, AMO was the leading time series to AMOC. So AMO seems to determine the variability of AMOC. But after 1975, at the end of so-called hiatus period, this leading relation were reversed, and AMOC was leading and AMO was following. The hiatus period was a period in which the trend in now was essentially reduced or set to zero. When we are talking about long-term variability, decadal variability, and especially if we want to move from surface to ocean interiors, where the vast majority of heat content and the dynamics is included, say, we do need more than simple a satellite observation of sparse hydrographic observation. And unfortunately, only recently we have the technical capacity and the ambition to do such kind of large-scale observational effort in order to guarantee a timely detection of variability of this quite crucial process for the climate system. And to observe variability in AMOC, as you see in this picture, huger amount of observing platform has been deployed from the Strait of Florida. This is the western array up to the African coast, and with some additional floats and moorings in the Middle Atlantic reach. So we have three arrays, one on the western side, the other one on the central part in correspondence of the Middle Atlantic reach, and the other one, the eastern array along the African coast. This array has been supported by UK, and I think there are other partners now, but basically is a UK initiative launched in 2004 and is still operational. And it has already gave the first important result. The first result was, and we'll see better in the next slides, NAMOC went in a state of reduced overturning since 2008. Sort of a change between the 2004 to 28 period and the period that came later, after 2008. When you have a reduced AMOC, obviously you have effect on the positioning and the shape of the Gulf Stream. The Gulf Stream has a northward shift and a broadening. The broadening could be quite I don't say obvious, but reasonable effect, since if you have less energy, the current is less strong, and the adjustment effect due to Coriolis force is reduced. And this brings to a modification of heat content and sea surface temperature due to this kind of concomitant changes. Here we are. This is the calculation of the meridian transport. So the AMOC calculation split in different components of the flow inferred by the rapid array observation. I want to go back again. You see, this latitude is 26. And as you see here, you have a sort of a recirculation partner here in correspondence of tropical gyre. Then you have the downgoing cold branch of AMOC, and also you have the Gulf Stream that goes in or brings in the heat content. So it's not simple to detect just purely looking at data, which kind of circulation we have above. But discriminate from the different processes active there. For example, you have the dense water here that changes and contribute are negative. So they are outgoing, is the coldest part. They contribute for some sphere drop, not that much. Then it's also a positive transport due to Ekman transport. So the direct action of the wind, which is also northward directed. What we are interested in here is the fact that we have the meridional or returning circulation that has a sudden jump in correspondence to 8, at least in the interpretation of Smith as all that published this article some years ago. And this is a decadal change, but you can see you have also interannual variability, which is quite well established here. On top of this, you have another time series, which is the recirculation due to the subtropical gyre, which is much more intense than the AMOC. And it's quite interesting to see that at least here, the dense water has the opposite correlation with the MOC. So the reduced heat transport northward increase the quantity of dense water formed. And well, a naive explanation could be that you transport less heat here, and so the water is denser, or starts as less denser water, and the formation processes are more effective in creating more dense water. Is true, I don't know. There are in reality some delays, or the advection time scale could be longer. So I'm not so sure that this explanation is the right one. It could be a concomitant effect of the changes in Ekman. You see here, Ekman has a reduced effect here. So the system is quite complex, and even simpler or naive intuition can be really misleading. What we can say instead, with some certain degree of reliability, this is quite clear. The variability has a variety of time scale superimposed. And this variability could have also have potential role to create rapid climatic change, at least in the past, because of its important role in bringing high latitude the heat. And not directly from data. The data explore only 15 or 16 years, not more. But in a simulation or climatic simulation, the tendency that appears in ocean atmosphere, a couple persistent models, is the fact that the intensity of AMOC is expected to decrease in 21st century. Essentially, this is the response to the global change. You have to take account also of the ice ocean interaction that also can play a role in determining or the weakening of this. And another point that has emerged from such kind of numerical simulation is the fact that the AMOC variability at the decadal scale is associated in we saw this also earlier. This is a confirmation of that. But what could happen in perspective? We talk about the risk of weakening of the meridional heat transport, overturning circulation, weakening. But will meridional heat transport stop? And this is point that arises some interest. Also, a film on the catastrophe generated, or the catastrophic cooling generated in New York, ascribed to the fact that the Gulf Stream stopped and has been on screen some 10 years ago. So it's something that also hit or suggested something interesting also at the popular level. And popularization science in this case should clarify that the things are not so simple, probably not so dramatic as the film depicts, but they can have serious consequences. And the question is provocative, but the experimental concept that we can do just putting together the single component of the whole picture, well, can make us think about quite seriously. It's not only a joke, it's not only a film, but is a serious scientific question. And we can see that the salty Gulf Stream water bifurcates here. Part goes down, part reach the Scandinavia and North Europe, and then its path goes northward and recirculate in the Arctic Ocean and mixed with Arctic water, creating the East Greenland current that goes down. And this in this process, the water gets denser and denser, and progressively reach the area where densification, sudden densification process takes place, both in open ocean spots, as we saw before. There are specific area where the ocean physiography, the current, strong wind forcing, and the peculiar cyclonic circulation favor the open ocean convection. In addition, also the dense water formation on the shelf, maybe the denser water formed on shelf, not in open ocean, also contribute to that. In the preconditioning here means that the warmer water is less dense, because lose temperature, is transformed and has the right density to be cooled, to contribute or to be transformed in dense water. This is the regular process. But what happens if we don't have less the surface water less salty? For example, due to the global warming, you have ice melting, and Greenland and North Pole floating ice are losing mass in unprecedented pace, and this freshening has an impact for Greenland ice to the sea level, and but both contribute to freshen also the surface water. This means that you have a surface layer, where the buoyancy is increased, the density is much less than before. This, in turn, is not mitigated, this freshening, by the contribution of salty water due to the Gulf Stream. Our hypothesis is the Gulf Stream is reducing, something that has been already shown or suggested by the rapid observation and inferred by the long-term climatic simulation. So as a hypothesis, we have for sure, with the increase of the global warming, have less salty water due to the freshening of ice melting and the reduced salt contribution by the Gulf Stream. So the net effect is that the water that is usually conveyed from this Arctic area into the formation zone could be maybe no longer so dense enough to sink, however much it cools. So even if the forcing fields are not much different from the present one, the buoyancy content of the upper layer is too high to make the water denser enough to sink. And this would affect the formation of North Atlantic deep water. North Atlantic deep water, I recall you, is a complex of several water masses formed by deep convection in Labrador Sea, and also in the shelf formed on the Greenland Island coastline ridge. And if this water is not dense enough, eventually could stop, and this means that the thermoline or the thermodynamical engine that move the meridional heat transport would decrease, and again as a positive feedback in the reduction, the further reduction of dense water formation and its characteristics, and reducing the density signature. And a rapid drop also in temperature, in winter temperature, is also expected, because no longer the MOC is in force, and the meridional heat transport, or the branch of the Gulf Stream that reached Europe, will be strongly reduced, and obviously the ocean atmosphere exchanges will be not so effective in keeping the Scandinavia and Northern Europe warmer as is used to. the stopping mechanism most probably is an extreme scenario. More realistic one suggests that there will be a decrease, and potentially even now what is happening is the fact that the reduction of the heat transport in the northern part of the Atlantic is already in place, but this is also this signal is somehow smeared out by the fact that you have global heating. And so I remember a recent paper by Ransdorf group that shows that the rate of change of surface temperature is different, not the absolute value. So all the North Atlantic is getting warmer, at least in surface, but some areas are less prone to increase their warming. And to summarize, could the meridian heat transport could stop, most probably would be reduced. This could have an important effect on Europe variability, and also on ventilation of the dense water of the Atlantic and the global ocean. And this is something that for the future. But what happened in the past? Is the freshening effect so important for the dense water formation, or is something that is purely an academic speculation? And there are some, well, interesting climatic records that show that this is quite crucial as a parameter. And there was, we have to go back at least from 800 years ago. And we, as you see here in the cartoon, the conditions of the Canada coasts. You have a big lake called Lake Agassiz, which was dammed by large ice sheet that act as a natural barrier between fresh water and the Labrador Sea. And 8,000 years ago, we were about to face the lower tail of the ice age, last ice age. And progressively, the large ice sheets that cover the northern part of and southern part of the hemisphere decrease and shrink. And in the case of the ice dam that gave the barrier, or that formed the Lake Agassiz, collapsed. Well, catastrophic outflow of meltwater covered all the Labrador Sea, and means about 5/3 of half a year, was sufficient to severely disrupt the hammock and its poleward heat transport. And the record of that has been found in climatology for that. So this is an extreme event that takes place in an abrupt way, quite differently than what we can see in the future, but still the take-home message suggests the fact that such kind of process can severely affect the circulation of the North Atlantic. There is another interesting point to explore. We saw the effect of AMO and AMOC, or the correlation between the two. We saw the importance of NIO in driving, at least at long time scale, the variability of these two systems. Also, we can also explore the connection between the decadal variability of AMOC with the dynamic of the subpolar gyre. And you see here two average of the steric sea level trends. A steric sea level trend is the thermal expansion of the water column, and here they are subtracted all the other dynamical component. So this is due to only the heating or cooling of the water column. This is called the steric sea level. And there are also some two different time data set. One is obtained by satellite, the other one from observation, average in two periods, same for the two data set, one in 1993-2004, the other one 2005-2060. The area in which the signal is stronger is identified by a square. You can see here. And in this area, in the 4 time series, has been averaged and plotted in this plot. And you see here that you have more or less the same. You have a cold, fresh, strong subpolar gyre in the period of the 90s. Then you have a warm, saline, and weak subpolar gyre in this period. Then again, cold, fresh, and strong subpolar gyre. So a long-term variability. This decadal variability in subpolar gyre is connected to the cooling, strengthening, widening, and on the opposite, the warming, weakening, and shrinking related to the expansion of the dynamic steric sea level. So if the water column gets warmer or colder, then we have this kind of anomaly in the circulation of the gyre, and is quite interestingly that this variability mimic quite well the dynamic of the Atlantic meridional ocean circulation. Okay, we saw that there are variabilities at the decadal scale, which are more and more, whose role is more and more emphasized by long-term simulation and the decadal time series that are already available. But there is not yet not yet a consensus on what are the relative contribution of the different proposed mechanisms to Atlantic climate variability. Everybody understands then when you move toward decadal scale, you do need to consider not only ocean or not only atmosphere, but the both system together. But which is the relative importance of the contribution? This is not clear. Interaction with atmosphere, stratosphere, tropical influences, or interaction with ocean, which is the role of atmospheric intrinsic variability due to the storm track, tropical forcing, how they sell. The now index is a quite important one. Or which is the role of the ocean interaction adjustment to this atmospheric variability, mediating by the dynamic of the ocean mixed layer, or the response of the ocean to the changing wind stress curve pattern due to the changes in atmospheric circulation. Also, we understood that now is a primary source of variability of equatorial tropical Atlantic, possibly related to the remote forcing or teleconnection with Pacific ENSO. So there are hints that all of them has or plays a role, but say comprehensive picture that explains this variability is no longer available. So we have the evidence, not yet a full or convincing explanation for that. The processes are there, and nobody objects for them. But what are the dominant processes? In which condition one prevail compared to the other? How they interact, and which is the feedback? This is still under investigation. What is interesting is the fact that even if we are conditions that may be similar to at least in terms of area and latitude, then we could expect to have some ENSO-like process. But the confined extent in the zonal direction of the tropical Atlantic is too small to lead to strong ENSO-like coupled ocean atmosphere modes. Possibly some coupled interaction may exist, but at the moment we don't have any clear evidence for that. So the Atlantic variability at decadal scale is not yet fully explained, even if some correlation and some links have been already soundly detected. Staying still at the same scale, but in a different ocean, we talk about another large-scale decadal oscillation. It is dubbed the Pacific decadal oscillation. The Pacific decadal oscillation is again defined by the leading EOF mode of the surface temperature anomaly in the North Pacific, and the area considered as polarwards of the 20-degree north. This picture is the Sst Anomaly in red is positive, in blue, as usually, is negative. Sst anomaly is obtained by removing the climatological annual cycle and also the global mean Sst anomaly to detrend the global warming. So we have to subtract the global warming, then you calculate the seasonal cycle, and then you remove both from the SST. So do you have a pattern which doesn't reflect changes due to global change, nor the variability due to the seasonal cycle that we know at this latitude is quite relevant. We have again the concept is similar for this kind of indexes, and or this kind of pattern when we have a positive phase and a negative phase. The positive PDO positive phase corresponds with a negative anomaly in Central Western Pacific up to the Japan. The stronger negative spot is in the Central Pacific, while we have a positive Sst anomalies in the Eastern North Pacific along the west coast of North America. Is a typical shape that characterize the Pacific decadal oscillation. Again, we have the possibility or a natural way to represent such kind of evolution is, as I told you, this is the leading UF mode, and you may remember when you make a UF analysis, you pick the most significant, which is the first UF, and the first UF mode explain good part of variability at this scale, a long scale, and the index is, but it's a principal component, associated principal component that explain the time evolution of the first UF. UF analysis, as I already told you, as an important way to discriminate spatial to temporal variability, and moreover, can associate the variability of the space, or spatial variability, to single time variability. So the variability in time is depending only on time, not on space, and the variability is equal for each point of the space taken into account by the analysis. As you can see here, you have variety of oscillation at a higher frequency, but if you look at a broader scale or longer period, smoothing the annual data, gives, well, the interpretation gives, or there is a consensus to find two full PDO cycle in the past centuries, even if you can have more indirect evidence in the last millennium for this kind of variability. But the direct observation keep track of two full PDO cycles. And the cool PDO regime prevailed from 1890 to 1924, which is more or less here. Then you have a warm period until 1925, 1946. Then again, well-formed, well-established negative phase from 1947, 1976, and then again a positive warm period that goes from 1977 to mid-90s. Then there is a potential negative period. We don't know exactly what will happen. As I told you, this is the low-pass filter of this time series, and there are additional energy in the signal that is referred to shorter time scale from 15 to 25 years, which are not yet explained. Someone can say we are in the Pacific, and we have already seen in detail that there are variability at the interannual scale, like ENSO, that are more or less active in a similar zone, surely more concentrated on the tropical area, but also in the extratropic. We saw that ENSO has an important influence on the climatic condition and also on the circulation. So, which are you sure we have two different processes? There are three main characteristics to say so. First, the 20th century PDO events persist for 15 to 25 years, while typical ENSO events has a much lower duration, from 6 to 18 months. And the other point is that the climatic fingerprints of PDO were most visible in the extratropics, while El Nino has the typical cold, warm tongue at equator. And this is more an excusation than an explanation. The mechanism causing PDO variability are not known, while the causes for the ENSO variability are, as I tried to explain you, relatively well understood. Not the full process is understood, but largely the ENSO phenomenon is understood the model. So far, so good for what regard PDO. And there is an extension of PDO. PDO is related on the northern Pacific. And there is another mode of variability, that is the interdecadal Pacific oscillation, is a climate variability pattern that has interdecadal time scale, as a quasi-oscillation that goes for 40 to 60 years, mostly in the Pacific basin, as interpreted as Pacific-wide manifestation of PDO. And it means that you are no longer related to the North Pacific, but you include the whole Pacific. And the climatic impact of SST precipitation have been found over Australia, Southwest US, and other regions. So there are relationships between this index or this oscillation and the climatic response in the surrounding region. You see here, we have, or you can find in two different composite of SST calculated in Hadley SST time series in European and other European data sets for two similar periods, and both show a clear the shape that we see here, which are similar to what we have found in case of the PDO, but a similar pattern replicated in the southern ocean. So we are a wiggling effect going to the maximum, minimum, maximum along the day line, and this is respected very well in the two data sets. So is data source independent, which is good for to understand, to consolidate or to corroborate that this oscillation is present, irrespective which is the source of data sets used. And the definition for the IPO index is that in this case is the second leading Moore for the 3-year moving average SST calculated in this band. And obviously here you have also the signature El Niño, and the time series associated to the principal components. Here you have the annual data, then you have the smoothed area, and shows this quite an evident oscillation. And this, to compare, is a time series of the sea level pressure calculated in the same areas, and see that the two goes quite well together. So the IPO index is quite a nice way to to extend the concept of PDO to the global Pacific Ocean. My personal question, I have no answer. Which is the role of the ENSO or the El Niño La Niña in this IPO index? Is the two somehow connected? Well, I have no answer for that. Again, when you have such kind of long-term oscillation, the question is how to calculate index to simplify the understanding, to better follow or discriminate the states between the two negative and positive conditions. And in this case, what has been proposed as the soundest way to calculate an index, the TPI, has been calculated using 3 zones. One in the northern Atlantic, the other one is the Pacific, sorry, and the other one is the Equatorial Pacific, and the other one, and the third one is in the southern hemisphere near the Australian coast and New Zealand area. All right, and TPI is based on the difference between SST anomaly, average of the Central Equatorial Pacific, the average of SST in Northwestern or Southwest Pacific. Here we have in plate the temperature anomaly indexes using different 3 different data sets, 2 for Hadley Center, the other one for Europe. And then you have another index calculated by UK Met Office, and you see the TPI seems to be very good performance and exhibit a strong correlation with the IPO, the index calculated by UK Met Office, which quite complex to calculate and simple. TPI is simple to be compute, and also is consistent with the indices used to track El Niño southern oscillation, such El Niño 3-4 that they have already heard. So far, so good for what regard Pacific Ocean. We saw they have a large scale variability, a decadal time scale, both in north and in the of the whole basin. And I want to conclude with something I know directly for my direct experience better, which is the Mediterranean. Also, Mediterranean has exhibit variability which is not easily referred as the typical oscillation cycle that we saw in the other basin. Often Mediterranean has been told be called as a miniature ocean, where all the processes are present. The scale is smaller, so we can study the effect of large scale processes at much smaller scale. So the processes are faster, easier to be detected. Unfortunately, the circulation in Mediterranean is quite peculiar. It does not respond to the same dominant driving forces that are acting in the Atlantic. First of all, you see the Mediterranean is an zonally elongated basin, and the circulation, as you see here, traditionally goes from west to east and not north to south, like in the meridional overturning circulation, and is driven by wind, and in this case, modulated by wind, and is driven by thermoline forces. The major thermoline force here, obviously, is the buoyancy loss or the buoyancy gain due to salinity, not to the temperature. So, being zonal, the heat fluxes are more or less similar, but evaporation and precipitation minus rivers play a major role in creating dense water. So the relatively fresh water coming in the basin. This is the traditional picture, well established until the 90s. Every textbook has this kind of picture. So the Atlantic relatively fresh water of Atlantic origin enter Mediterranean, cross with some branches. The whole basin reach the eastern part. In this case, gets denser and denser. Then we have a little cooling, and the water is goes down and go back, closing the main thermoline cell. But this is not the whole story. Here we have, for example, in the Adriatic for the East Mediterranean, and in the Gulf of Lion for the Algero-Provençal basin in this area, you have zone area of deep water convection, the same kind of deep water convection that takes place in the Labrador Sea and in the Immergate Basin. So we have a mid-latitude conditions that create the same cooling processes that form the dense water. Since the two basins are separated by the shallow sill, the two dense water are formed and replenish the deeper part of the ocean, of the Mediterranean Sea separately, and the two water are not connected. This was the well agreed and well established a picture that was accepted. But in early 90s, geophysicists made some making some observation of temperature in the upper sediment temperature gradient, so a very anomalous signal, and typically the sediment release temperature to the bottom seawater. In this case, the temperature gradient was the opposite. So the water is transferring energy, thermal energy, to the sediment. Was quite strange things. And after a while, the whole Mediterranean community gets alerted and get crazy for that. And at the end, there was a first explanation that was progressively refined, but after 1987, last big poem cruise that make a very nice picture of the Mediterranean circulation with the mesoscale jets and the dense water formation. This similar pictures, more complex, but similar picture to this one. Then after this, we with a series of data, we ended up in a different picture. So the major difference here to here is that the Adriatic no longer produced the dense water. Instead, the dense water has been produced by the Cretan Sea here in Aegean. And the Atlantic water, or the water, modified Atlantic water, has been diverted into the Ionian Basin. Ionian Basin is this one, and a branch goes there, and a limited water reach this area. And this changes a lot the temperature and salinity conditions of dense water. And this variability has been dubbed as the East Mediterranean Transient, that occurred in the Aegean Sea, but influenced the whole Eastern Mediterranean. And the major change, as I told you, the major change in circulation was the change in deep water formation. But and it was quite clearly seen because have a concomitant increase of temperature and salinity. So the density was higher, but the salinity was also higher, and temperature was higher. So compared to the Adriatic, the characteristic of Aegean Sea water were very, very clearly seen. And also the spreading was quite important. It had also the effect to be rise or to lift up whole intermediate water column water masses that were present in the Ionian Sea, because in this period, in 7 years, the mechanical, the thermodynamic engine acting in Aegean Sea was able to produce 10 times, roughly 10 times more dense water than the Adriatic Sea in the same, that it was used for in the same period. And so the replenishment of this water, dense water of the Mediterranean on the Ionian Sea was very effective, and was saw a very strong uplift of this of the water properties, or the water masses together with the proper water property in Ionian Sea. And afterward, as I show you here, you have the return current that crosses the Sicily Strait and reached again the Western Basin. During this path, the signature in temperature salinity and in nutrient, for example, or oxygen, has been also detected in the Western Mediterranean. And so there's also the Western Mediterranean, Eastern Western Mediterranean transient. So the effect, remote effect on the intermediate water conditions in the Western Mediterranean due to the changes into the in the dense water formation mechanism acting in the eastern part. Why we talk about transient and not oscillation or internal variability or something like that? As most probably because a similar event has been also present in the past, but has different characteristic and different intensity. In this case, and a careful analysis of the forcing field and the prevailing surface intermediate circulation in the area lead to propose a multiple causes for concomitant multiple causes that would happen together in order to change this the dense water formation area from the Adriatic to the Aegean or to Cretan Sea. First, a block, so a reduction of the modifiers Atlantic water inflow in the Eastern Mediterranean due to the presence of permanent or semi-permanent strong anticyclonic blocking system southward Crete. And this means that less fresh water has been brought in the eastern basin, so an accumulation of high salinity water was the net effect of that. There were a couple of very severe winter in the Aegean Sea, especially in early 90s, that enhanced the heat loss in this area. And concomitant with that was the change in the surface circulation of Ionian Sea from anticyclonic to cyclonic, diverting part of the fresh water of Atlantic origin into Ionian and not in the Eastern Mediterranean. It's still unknown whether similar transit occurred in the past. As far as we know, there is no evidence for a similar or so strong effect, but similar event may be happened. But we don't know if the forcing were similar, the same, and also where was which was the dominant one, and on the relative importance of them. Being connected to the heat loss, so to the forcing field, and input of vorticity by storm track during winter in the Ionian Sea possibly can also influence the surface circulation. It's not surprising that recently there was a proposal that this Mediterranean circulation destabilization that gave way to the East Mediterranean transient occurred during positive now and negative AMO phase. This is a recent paper on that statistical correlation, but could partially explain this process. Okay, I think I finished for today, and as usually, I give you the slide, and partly of this lecture is already incorporated in the note that I sent you yesterday. If you don't have any question, I stop here. In any case, I'm available to be, you can reach me on my email. Feel free to send me any comments or question. And tomorrow is the last day to solve your big problem about ocean variability. So don't be shy. Ask me any question you may think is important to clarify, or even suggestions are very well accepted. Okay. Thank you for your attention, and I think time is over. Bye-bye. Have a good week, and see you soon on the screen. Ciao.
Ciao.
Buona giornata.
Thank you.
Ciao.
Bye, thank you.